Welcome to the next set of video notes. In this section, we're going to look at how to do a hypothesis test if you are comparing information about two population proportions. So the idea behind this is instead of just looking at what is the proportion of all people that prefer, let's say, chocolate ice cream, we're going to look at comparing like men and women, or older people and younger people, or you could do different socioeconomic classes or races or countries of origin, anything you could think of where you're trying to do some sort of comparison. So I'm going to use the example throughout these notes of looking at men and women and their preference of chocolate ice cream over a different flavor. So recall from our previous sections the equations for p hat, the mean of the distribution of all possible p hats, the standard deviation of p hat, and the z-score equation. Okay, so we're going to have some variations on each of these. So when you have two population proportions, we have a p hat 1, which is the sample proportion from the first population. So let's say this is the sample proportion for the men only. So we would find the number of men that say they prefer chocolate and divide that by the total number of men. P hat 2 is going to be the sample proportion for the second population. So let's say women. So we'd find the total number of women that said they prefer chocolate ice cream over the total number of women that we sampled. We have an overall p hat, which is a pooled sample, so it's overall what is the proportion of people who say they prefer chocolate ice cream. So the number of men that said chocolate plus the number of women divided by the total sample size that we took. And this is the standard deviation equation for the difference between two proportions. I'm not going to read that out loud, but it's there for you to reference. And then the z-score equation is, as you see here, again, I'm not going to read that whole thing out loud. We aren't going to actually be doing this hypothesis test by hand. I'm actually just going to go straight into the calculator when we get into the example to show you guys how to do these tests. So setting up the null and alternative hypothesis for the difference between two proportions. So a left-tailed test, our null is going to be P1 equals P2, and the alternative is going to be P1 less than P2. So the null is saying we're assuming the population proportion of men that prefer chocolate ice cream is equal to the proportion for women, but the alternative is saying that men prefer chocolate ice cream less than women. The right-tailed test, the null is exactly the same as before. The alternative is P1 greater than P2. So for the example I've been using, this is saying that men prefer chocolate ice cream more than women. And finally, our two-tailed test, the null, again, P1 equals P2, and the alternative P1 is not equal to P2. So this is saying that men and women do not prefer chocolate ice cream in the same proportion. So to do a hypothesis test between two population proportions, the first thing we want to do, I'm making this an official step here because it's going to be extra important now, is to identify the important information and the values. So making sure we recognize that this number is for the first population and this is for the second and this is for the first, identifying all of that important information. Then we're going to write the null and alternative hypothesis, calculate the test statistic and p-value, and this step we're going to do solely in our calculator. We're not going to do it by hand at all. And then finally write our conclusion and interpretation. So let's get into an example. So in clinical trials of Nasonex, 3,774 adult and adolescent allergy patients were randomly divided into two groups. The patients in group 1, the experimental group, received 200 milligrams of Nasonex, while the patients in group 2, the control group, received a placebo. And a placebo just means they received a sugar pill, but they weren't told that. Of the 2,013 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the control group, 368 reported headaches as a side effect. Is there significant evidence to conclude that the proportion of Nasonex users who experience headaches as a side effect is greater than the proportion in the control group at the alpha equals 0.05 level of significance? So I'm going to go through and I'm going to highlight all of the important pieces of information that I found in this problem. And there it is. So 3,774 adult and adolescent patients were divided into two groups. There were 2,013 patients in the experimental group, 547 reported headaches. There were 1,671 patients in the control group. 368 of those reported headaches. We have the word greater than, which is going to let us know whether we're doing a left, right, or two-tailed test. And our level of significance is 0.05. So now I'm going to go ahead and write down the numerical value I found and the symbol that that value represents. So 2013 is going to represent N1. That's going to be the first population. 547 is the number of people that reported headaches from that N1, from that experimental group. So that's X1. N2 is the 1,671 people in the control group. X1 is the 368 people that reported headaches from that control group. And alpha equals 0.05. So now step 2, write out my null and alternative. Because I saw the word greater than in the problem, that tells me that I'm doing a right-tailed test, because that means that I want to see is the P1, which is the proportion from the the proportion from the experimental group, is that P1 bigger than the proportion from the control? So is the experimental bigger than the control? Now step 3, in the calculator, you're going to go to stat, you're going to go to test, number 6, 2-prop z test. X1 is going to be 547, N1 2013, X1 368, N2 1671, and then the last step it asks for is P1. Are we saying that's less than, greater than, or not equal to? Not in that order, however, and we're saying it's greater than. So I showed you this in the PowerPoint, and so now I'm going to exit the PowerPoint real quick, and I'm going to show this to you in the calculator. Okay, so I'm going to hit stat. I'm going to arrow over to tests. I'm going to arrow down to number 6, 2-prop z test. Hit enter. Okay, my X1 is 547, N1 2013, 368, 1671. We're saying it's greater than P2, and we're going to hit calculate. So here we make sure that the top line matches our alternative. So does our alternative say P1 greater than P2? And it does. Here's our z-score, 3.6021, and here's our p-value, 1.5785. But then notice the e to the -4. I'm like, that's not right. E to the -4, so that means we're going to move this decimal place 4 places to the left, so we're left with 0.02. And then it gives you the p-hat, the p-hat1, p-hat2, p-hat, and your sample sizes again. So let me go back to the PowerPoint. Oh no, it started from the beginning. I'm sorry. I didn't know I was trying to do that. Why isn't it going? It doesn't want to, it's not going forward fast enough. Ah! Okay, so here's where we're at. So we found our Z, 3.6021, and that had a p-value of 0.02. So we ask ourselves, is this p-value too low to be possible? So is 0.0002 less than 0.5? Yes, it is. So if p is low, you're going to reject HO. So we're going to reject the null hypothesis and conclude that the proportion of Nasonex users reporting headaches as a side effect is greater than the proportion in the control group. And that is it. That is what you need to do a hypothesis test for two proportions. Okay, we're still comparing that p-value to alpha just as we did before. It's still calculating a z-score just as it did before. Just now that z-score equation is very different. So that is it for these